Good morning, everybody. Happy Monday. We've covered enough of the collision-related problems for now, so let's move on to something new. Here's a very generic problem involving some object that will explode into two fragments, which we'll call fragment A and fragment B. We want to figure out the kinetic energy for each fragment in part A, and then determine the percent of the total energy that each fragment receives if one is much more massive than the other in part B. Let's start off by using the conservation of momentum. The original object was initially at rest before the explosion occurred, so we're going to have 0 on the left-hand side. On the right, we'll keep it simple and say that the fragments fly off in opposite directions, with fragment A moving to the left in the negative direction and fragment B to the right in the positive. I'll move the negative term over to the other side and then solve for the velocity of A in terms of the ratio of the masses multiplied by the velocity of B. Now we can move on to the conservation of energy next. Here we have the sum of the kinetic energies of both fragments being equal to the total energy that's released by the explosion, which we'll just call Q. I'm going to take the expression for velocity A that we just solved for and plug that in here. We want to square everything inside the parentheses here. And notice we'll end up getting a mass of fragment A squared in the denominator. And one factor of that will cancel out with the mass of fragment A outside the parentheses here. And with that cancellation, here's the result. Notice there's some common pieces between these two terms on the left that can be factored out. There's 1/2 in both, along with a single portion of the mass of fragment B, as well as the square of fragment B's velocity. Let's go ahead and pull those outside next. At this point, this coefficient outside the parentheses should look pretty familiar. It's the kinetic energy of B. We want to solve for that, so we'll need to divide both sides by what's in the parentheses here. Once we do that, the denominator on the right is kind of ugly, so we'll need to take a moment to rearrange it into something that looks a little nicer. We can multiply 1 by a special factor of 1 in order to combine what's downstairs into a single fraction. And remember, when you divide by a fraction, it's the same thing as multiplying by the reciprocal of that fraction. So the form of our kinetic energy of B will look like this. And we can even rewrite the left-hand side so that it's clear what we're referencing here. And now we have 1/2 of part A complete. To get the other half, let's go back to step 1 in the energy equation and then plug in the expression for the kinetic energy of B. I'm going to subtract it on both sides to isolate A's kinetic energy on the left, and then we can also factor out Q. Again, we're going to craft another common denominator between these two values inside the parentheses by multiplying 1 by a special form of 1. And following that, we can combine them, and notice we're adding the same mass of fragment A that we're subtracting here in the numerator. So those two pieces can be removed, and we're left with the following ratio. And with that, part A is now complete. In the next part, we're going to let the mass of fragment B equal 4 times the mass of fragment A. Let's start with the kinetic energy of A first. Here you can see that I've replaced the mass of fragment B everywhere in this equation with 4 times the mass of fragment A. The terms in the denominator will sum to 5 times the mass of fragment A, and we can even cancel out the mass variable entirely because it hangs out in the numerator as well as the denominator. The percentage equivalent of 4 divided by 5 is 80%. So this means that the lighter piece, fragment A, will inherit 80% of the energy from the explosion. And this leaves the remaining 20% for the more massive piece, fragment B. Part B is now complete and the problem is finished. Stay tuned for the next few videos where we apply this idea to particle physics decay and some exploding fireworks. I think some of you will enjoy that. As always, thanks for watching.